So can you hear me, Ranjan? Rajna? Mic is turned on. Okay. So we'll discuss those topics. Continuous functions, function, and countability, axioms. And we also solve some problem from this previous class, quotient space. We also see a particular topic which is called Kuratos is closer. So let's start with continuity. What is continuous function? We already know continuous function means it is a map between topological space. So x and y both are, those two are topological spaces. Okay, map between two topological spaces. It satisfies the property such that additional property is f inverse of any open set is open. This is open in X for all open set V in Y. Okay, this is the definition of continuous function, and we know that this is actually equivalent to saying f inverse of closed set is closed. Some closed set is closed in Y in X for all closed set F in Y. And this is also equivalent to the definition we are familiar with. So the definition is for all x belongs to x, given any neighborhood v of x, probably vx is better notation. Vx, any neighborhood vx, not okay, v of fx. I am taking a neighborhood of the image fx. There exists an open set ux or open neighborhood of x. Okay, open set or open neighborhood of x. That means an open set which contains x, such that f of ux containing vx. So this definition we already know, and those are actually equivalent. Okay. And this is also equivalent to another thing. We know that in metric space, we know a function is continuous. It means we can define in terms of sequence. That is, it takes limit points. That is, if xn converges to x, the image f of xn should converge to fx. This is an alternative way to define continuity. But the problem is that sequential criteria does not hold for any topological space. So instead of that definition, there is a generalization. This is continuous. It means f of a closure containing f a closure. So if we choose some element from closure, it sends to the closure of f a. Okay. So that is the similar thing. That is, in particular, we get if xn converges to x, this will imply f of xn. This this converges to fx. You can say this is a particular case. Xn converges to x means xn belongs to, suppose x is an element of a, then xn belongs to a closure. Sorry, x belongs to a closure. Sorry, xn are taken from a, then this means Ax belongs to A closure, and this means this will imply that fxn are taken from fa. So fxn converges to fx means fxn, the limit fx belongs to fa closure. Okay, so that's why this is the generalization of that idea. So those are equivalent way to say if a function is continuous or not. Now, after that, the topics comes is homeomorphism. So what is the meaning of homeomorphism? Homeomorphism means if two topological spaces are same or not. So in set theory, we know two set are same or not. It can be defined by cardinality. That is by bijection. A bijection means those two sets are same. Okay, and in group theory, we know something two groups G and H, those are same or not. It is determined by a isomorphism. So two groups are said to be isomorphic if there exists a map. Now the map should be not any arbitrary map. This is group homomorphism, which is also a bijection. Okay. Similarly, we have seen those kind of thing for vector space and all those things. Now, that idea for topological space, this kind of isomorphism or not, that idea is named as homeomorphism. So homeomorphism means so a map f from x to y. Now a map is means a continuous map. A continuous map from x to y between two topological spaces is said to be homeomorphism if there exists a map in the reverse direction. So there should exist a map from the reverse direction. This should be continuous if there exists a continuous map such that f compose G is identity on Y and G compose F is identity on X. So here we are not saying that F is continuous. In addition, F is a bijection. We are not saying that property only. We are saying more. That is, there should exist a map in the reverse direction. So note that in vector space isomorphism, a map from V to W, this is called isomorphism. First of all, it should be a vector space morphism. Okay, a vector space morphism, a homomorphism, which is bijection. So in that case, this property is okay because bijection means there exists a map in the reverse direction. A homomorphism in the reverse direction. That F inverse defines a homomorphism. But in topological space, a continuous map which is bijection, that may not imply that the inverse map F inverse from Y to X, this map may not be a continuous map. That is the problem. So that's why in addition we also need to include this property. The map in the reverse direction, this should be continuous. Okay. So if you say a continuous map which is bijection, that may not imply a homeomorphism. The reverse direction map should be continuous. Okay. We have already seen that identity map from X to X. So here, if you take indiscrete topology, if in the second place in codomain, if you take discrete topology, So let me write in a reverse direction. So example, identity from, this is actually non-example, because identity, first let me see the example. Identity from x with discrete. So x has more than two element, otherwise it will not hold. X with discrete topology, and now here we are considering x with indiscrete topology. So you can see that identity is actually bijection. Identity is always bijection, and this map is actually continuous because identity inverse of any open set. So in discrete topology there are two open sets. One open set is empty, another is X. So identity inverse of empty is empty, identity inverse of X is X. So both are open in discrete. But is it a homeomorphism? It will not be a homeomorphism. Why? Because the reverse direction map, that is also identity map. Identity inverse is identity. That map from this indiscrete to discrete is not continuous. Okay, that's why the definition is like this. So the reverse direction map also need to be assumed a continuous map. Otherwise, this is not a homeomorphism. You can see that those two topology are different. Indiscrete has only two open sets, empty and X, but discrete has lots of open sets. So though the simplest kind of map is not homeomorphism if you don't assume this condition. Okay. This is non-example. This is continuous but not a homeomorphism. Okay. Identity map from x comma indiscrete to x comma discrete is not continuous. Since this is the problematic part. Since this is this. Now examples. So let us see some example of homeomorphism. So Prajna, can you hear me? Hello.
Yes, sir.
Okay. Everything is okay. So example of homeomorphism. One example is any interval 0, 1, and the particular interval 0, 1, this is homeomorphic to any arbitrary open interval a comma b. Can you see this? How can we define a map? So two space x and y are said to be homeomorphic. So the notation is x, that isomorphism notation. If there exists a map, there exists a homeomorphism. Homeomorphism f from x to y. Okay. So can you construct a homeomorphism from 0, 1 to AB? Can you construct a map?
Yes, sir. So if we consider a line with the slope mod of a minus b,
Yes,
and
exactly. Sorry, exactly that map. Slope should be b minus a. So can you explicitly write the map? It should be like this: a plus b minus a times x, right? At x equal to 0, it gives me a, and at x equal to 1, it gives me b. So this is continuous because it is polynomial. So can you find a map in the reverse direction? So let us solve this equation. A plus b minus a times x equal to 1. Okay. then can you see that x equal to y minus a by b minus a?
Yes.
Okay, so the reverse direction, the map in the reverse direction will be g from AB to 0, 1, and it is given by g of y equal to y minus a by b minus a. So both are continuous. This is continuous, okay, this is also continuous, because polynomial and those are continuous. So here we are considering Euclidean topology or usual topology, that is subspace topology of the usual topology, okay, those as a subspace of R with usual topology. So that's why x, and now another thing we need to check, which is already checked here, right? F compose G is identity and G compose F is identity. It can be easily checked. Therefore, this is true. Therefore, homeomorphism. So this is done. Now, what will be the second example? If this is first, then you can see by the same argument, closed 0, 1, this is homeomorphic to closed interval AB. Is it clear?
Yes.
Okay. Another example is, you know that if you take this map 1 by x, if x equal to 1 by x, then at t equal to 1, its value will be 1. This is at 1, its value will be 1, and at 0, it will be infinity. So, using this example, you can see 0, 1 is homeomorphic to 0, infinity. It will goes to infinity. At 0, it will goes to infinity. So, what will be the map? Define the map from 0, 1 to 0, infinity by fx equal to 1 by x. Sorry, this is not 0, infinity, it is 1 comma infinity. So to get 0, infinity, just subtract 1. Okay, that will work. So this is for 1 to infinity. So can you construct the map in the reverse direction? What will be that map? What will be that map? Inverse of this f. This is f. So yes, what will be there? So y equal to 1 by x, then what will be the value of x? It is 1 by y, right? Exactly. So gy should be 1 by y. The same map works. So again, you can check f compose g is same as g compose f. Those are different identities though. F compose g is identity and g compose f is also identity. So this is actually identity on 0, 1. This is identity on 1 comma infinity. Okay. So here you can see those two seems different. From geometry, those two are different because it has length 1, it has length infinity. Right? This interval has length infinity. But if you consider topology, those two are same. You can go from this topology through to this by this function. Similarly, you can, if you know the topology on this, that gives the same kind of thing. So in topological space, stretching is allowed. You can also construct another homeomorphism. There can be lots of different homeomorphism. For example, this kind of homeomorphisms are linear kind of thing, right? You are just stretching and shifting, but you can here you can see that homeomorphism actually non-linear. Similarly, there can be lots of different homeomorphism from this. Okay, so let me give an example of homeomorphism. For this, either you can use this homeomorphism, just 1 by x minus 1 for this, and similarly for minus infinity comma 0 you can use this kind of function 1 by x plus 1, or you can also use this map f from minus 1 comma 1 to r. Just define uh, yes, at x equal to 1 you want infinity, right? So you define fx equal to x by 1 minus x. So at x equal to 1 it is like you are expanding this 0 1 interval to infinity, and you are also expanding this 0 1 interval to infinity, minus infinity. So at x equal to 1 you want infinity, that's why you are defining it by, so you are not changing the direction, and you are dividing by this length 1 by 1 minus x. Okay, so it is not 1 minus x, it is mod x. Now everything is fixed. You can see this at x equal to minus 1, that will become minus infinity. Okay, so real number is actually minus infinity comma infinity. You can see that that morphism works. So can you construct the reverse morphism in the reverse direction? So again, we will use the equation y equal to x by 1 minus mod x. And you also note that x, when x greater equal to 0, y also greater equal to 0, right? So let us consider the case, let y greater equal to 0. Okay, for this case, this will imply y equal to x by 1 minus x, and this will becomes 1 by y equal to 1 by x minus 1. Therefore 1 by x equal to 1 by y plus 1, hence x equal to y by 1 plus y. Similarly, for y less equal to 0, there will be another case. In that case, the sign will change here, right? So in that case, we'll get this equation, x equal to y by 1 minus 1. So the map in the reverse direction, g from R to minus 1 comma 1, this map is defined by probably g of y. This is okay. G of y is this y plus y by 1 plus y if y greater equal to 0, or sorry, y greater equal to 0, and for y less equal to 0, this map is given by this. Okay, so those are few example of homeomorphism. Now, can you give an example of non-homeomorphic spaces to spaces which are not homeomorphic? Non-example. We already know that there are some spaces which are not same. Topologically, those two spaces are distinct. So, can you give some example? R with indiscrete topology. This is not homeomorphic to R with discrete. Is it clear why those two are not same? Because it has lots of open set, but it does not. Sorry,
Yes.
it is opposite. Okay, so it has empty and R. Those are the open set. Tau here. In this case, tau is the whole power set, which are not same. That's why there does not exist such kind of map, continuous map. You can also verify those kind of property if you know something about the topological space. For example, you know this is Hausdorff space, right? Discrete space is Hausdorff, but indiscrete space is not Hausdorff. You can also use those kind of property. Up to this point, we only know this is the only topological property. Up to this lecture, we are not familiar with other kind of topological property. We have already seen that length. From those example, it is clear that length, area, those kind of length, area, volume, those kind of geometric properties are not topological. Okay. So similarly, you can also see that R with usual topology is not homeomorphic to R with lower limit topology. You know that lower limit topology, this is actually finer. It is finer. Similarly, discrete topology is finer. And you also know that lower limit, no, there is no such kind of distinction. Both are Hausdorff. So I cannot use that property for this example. But you can use Hausdorff property for this example. R with, so you can distinguish this lower limit topology with the topology where the open sets are given by a comma infinity. Those are open sets. That is tau equal to a comma infinity. A belongs to R. This is also a topology on R. This is probably called ray topology because it seems like a ray. So this topology is distinct from the previous. Those two are not same because this is not Hausdorff. Those two are Hausdorff. Those are Hausdorff. But this is not Hausdorff. So those two are not same. Okay. Yes.
How is the lower limit topology Hausdorff?
Lower limit topology is Hausdorff. Why this is true? Okay, so you can see that lower limit topology has more open set, right? So suppose A and B are 2 point, A and B are two distinct point, then you can either choose this kind of thing, take A comma this, A comma some, let me take this as some point A plus B by 2. Okay, you can choose this interval, and similarly B comma something, B comma anything will work, B comma B plus 1. Can you see that those two are open non-intersecting open sets?
Yes, sir.
Contains. Okay. So those two are Hausdorff spaces. And another thing we already know that if something is finer than Hausdorff, that will be also Hausdorff, right?
Yes, sir.
Because it has more open set. The topology has lots of open sets, so you can use the previous one. That is, usual topology is Hausdorff, so you can also use that previous open sets. This kind of open set, right? That will also work. This open interval is also open in lower limit topology. We already know that lower limit topology is finite, so that is also open in lower limit topology. Okay. And this is not Hausdorff. Is it clear why this is not Hausdorff?
Yes, sir. This is clear.
Okay, because today will always intersect. There are lots of points where it will intersect. Okay, great. So those continuity is done. So let me tell you a property which always help to prove if something is continuous or not. You already know, but let me state. Pasting lemma. This is very helpful. Suppose f is a map from a1 to x, and this is f1, and there is another map f2 from a2 to x. Okay, we are assuming both map are continuous. Both are continuous map. Yeah. And also assume that, sorry, let me rename the domain as y. Also assume, let x equal to the union of a and b, a and a1 and a2. Then the question, those two map, from using those two map, you can define a map from x to y, right? From those two maps, because x is union of those two set. So on a1 and on a2, maps are already defined, and there is another thing that those two should agree on the intersection. Both are continuous map agreeing on the intersection. Okay, then you can always get a map from x to y. Now the question, is it continuous? The question, is f continuous? So pasting lemma says, this lemma, pasting lemma says yes, if both of a1 comma a2 are open, or both of a1 a2 are closed. Okay, so there is a condition which tell me that the induced map on x, that will also be a continuous map. either A1, A2 both are open or both are closed. So
Sir,
yes,
so is this for intersection or union?
yes. So on intersection that will be always true, right? A1 and F1 and F2 are continuous. So if you restrict some continuous map, suppose F is a map from A1 to Y. Now intersection is a subset, right?
Yes.
So if you restrict the map F on the intersection, so you from there you always get a map like this. So
Yes.
if this is continuous, this map will be automatically continuous.
Yes, sir. The
Why?
intersection is fine, but so this pasting lemma tells that even the union is continuous if both A1 and A2 are open or if both
Exactly.
A1 and A2. Oh, okay.
Exactly. It says the opposite thing. That is, so if f from x to y is continuous, then if we restrict on a1, then we get a map from a1 to y. That will also be a continuous map. It is very easy to see. Why? Because on the subspace, open sets are defined as intersecting with that subset, right? This is how subspace topology is defined. Okay. So it says the opposite thing, that is, we can also define it like. So we already know lots of example. For example, here you can use pasting lemma. That why this is continuous, we have not checked that this map is continuous, but pasting lemma says we know that close 0 to infinity, this is closed set in R, right? This is also closed. Okay. So G is defined piecewise. This is actually G1, so this can be thought as some G1y and this can be thought as some G2y, and both are agreeing at 0. You can see at y equal to 0, this is 0, this is also 0.
Yes, sir.
So the pasting lemma says this must be a continuous map. Okay. So we always use pasting lemma unknowingly. But what about if one set is open, another is closed? Can you use pasting lemma? Will it be a continuous map? So suppose A1 is open and A2 is closed. Can you use pasting lemma? Okay, let me draw this picture, then it is more easy to see. So suppose fx equal, you define a map from 0 1 to r. This is a1, this is fx equal to 2. Suppose this is the map, right? 0 to 1, this map is the fixed height. This is 0 to 1. Now define another map. This is a1. So define another map. A2 is now a singleton thing, and define fx equal to 3. That is at 1 we are defining fx equal to something like this. So from the picture, what is your suggestion? Is it continuous or not? So we have to map f1 and f2. Now combining those two, combining f1 f2, we are getting f from this open 0 closed 1 to r, defining by fx equal to x, sorry, fx equal to 2 if x belongs to 0 1, and if x equal to 1, this is 3. Now
This is not continuous.
this is
At one,
clearly not continuous. Exactly. So this condition cannot be, you cannot erase this condition. That is, we need both open. You cannot mix one open, one closed. That is not allowed. You can see in this interval open, if you think this as x, then one a1 is open, a2 is closed. The singleton thing is closed, this is open. So this is not allowed. Okay. Not allowed. Both are open, both. This condition is important. Now let me give another problematic thing. So there are only two open set. Can you use multiple open set, multiple closed instead of two? Can you use 3, 4, those kind of open set? Can you use?
sir, what do you mean by multiple open sets?
So f is defining partially on those two open set. Now suppose instead of 1, 2 there are n many open set. Will this property hold?
So I think yes, because even take so suppose there are A1, A2, and so on up to some n sets, then
Yes.
A1 union A2 they would also be open since arbitrary union is open. So I consider this new union as one set. So I can always reduce this to some B1 union B2, right?
Exactly.
Not sure about the arbitrary part, but if it's
Yeah.
finite, it can be done. I'm not sure about the arbitrary.
Exactly. Your argument is okay. For finite, this will work. This is one problematic thing. So instead of 2 for finite collection, that is a1 up to some n, if those are agreeing on the intersection, the conclusion works. It is just induction. So you can define continuous function piecewise. You can define on some pieces, and if those pieces, with respect to those pieces, fi's are continuous, then the whole f will be continuous. Now, can you do the same for infinite cases? So if we have infinitely many things, what about infinite collection? Suppose f of fi map ai to y, those are continuous. Now the question is f from x to y. If you glue all those functions, if you paste all those functions, then we get a function f from x to y. The question is it continuous? Is it continuous? What is your take on this? Will it be continuous? So the answer is no. Let me give an example. Suppose if this is a singleton Q to R, Q is rational. Okay, when when Q is rational, let me define. So this is FQ, and define F on Q on rational. Define FQ equal to 0. Okay, this is the singleton set, and I am defining FQ on Q is 0. And at irrational point, I am also, so infinite collection means uh, it is allowed to take uncountable set also. Okay, so on irrational, let me denote I. Fi on irrational values, Fi on this I, this is 1. Is it clear that FQ, Fi both are continuous function?
Yes, sir.
Yes.
But then the union is not continuous. Yes.
Yes. So pasting, so both are closed. You can note that those are closed sets. So it satisfies this property. We are taking closed sets. This property is satisfied. Hypothesis is okay, and there is no overlap. So that on overlap they agree, it is vacuously true in this case. But pasting, we are getting the function f from this real number to real number. Fx, this is 0 when x is rational. So here I belongs to irrational, complement of q, and 1 when x is irrational. Probably this function is called Dirichlet function, is it?
Not sure, sir.
Okay, you can see the name, probably Dirichlet. So this is not continuous. Can you show that this function is not continuous? So what is f inverse of 0? This set. This is closed set. What will be the preimage of 0?
The set of rational numbers.
Rational. So is it closed in R? This is closed in R. It is okay, closed in domain. Now is irrational closed in R? Not closed in R. Because you know that you can create lots of irrational points. There is a sequence of rational points which converges to irrational point. So that is, therefore rational number is not closed. Okay. So this is not true. Now what about for open? So in this example you can see I have used this argument, this point. But what about open? Can we allow infinitely many set for open? So if all those AIs or whatever, say A alpha belongs to the indexing set, if A alpha are open, alpha belongs to some indexing set, some lambda are open, then the conclusion is true. conclusion holds. This is an exercise. Is it? It is very easy. Why this should hold?
Well, again, since arbitrary union again would belong to
Exactly.
the topology.
Exactly. That is the problem where the argument for this closed set fails. Okay. So everything about continuity is done. Continuity and homeomorphism. Let me start from yes, countability. Okay. Countability axioms. So when something is said to be a fast countable set, so you know that countability means, okay, let me define fast countable space. A topological space, top space X, is said to be first countable if for all X belongs to X, there exists a countable collection Bx of open set corresponding to every X, every point in the topological space. There should exist a countable collection of open sets. Okay, so Bx is a set. um, Bx is a collection which contains some open sets. There are some U1, U2, some open set, maybe infinitely many, but that should be a countable collection. Okay, U1 up to some UN, and it will goes on. That should be countable. That is the point. Such that for all open sets U containing X, there exists B from this collection. B from this Bx, this collection with X belongs to B belongs to containing U. Is it clear?
Yes, sir.
So let me draw a picture, then it will be more clear. So choose any point X from this topological space X. And if someone gives me an arbitrary open set around this point X, then I have to give some open set from this collection Bx. Okay, so from this Bx probably something like this. Similarly, if suppose this shrinks further, then I need to give another open set from this collection. Okay, this is the definition of first countability. And for second countability, the definition is much easier. So let me first give some example of spaces which are first countable. So you know discrete topology on any set, on any arbitrary set, suppose discrete on any set, given any set X. X is any set. This is first countable. Is it clear why this is first countable?
Yes, sir. So it would contain even the singleton sets of
Exactly.
every element.
So for any given point x, x is always contained in the singleton x. Okay, so choose this bx as this. So the collection bx, it only contains this x, this set. Okay. Now, what about a metric space? Is it first countable? For any x, can you, yes, can you give me the open set around this point?
Yes, so you can find some R such that uh, so if x is some point, if I have some R, then I know that there's some open set.
Yes. Now, now the problem is this R may vary over real number. So if you choose all those bxr, if you choose this local basis as this bxr where R varies over all real number, then that collection is infinite, uncountable, right? Because corresponding to irrational number, you are also choosing some bxr element.
Oh, yes.
So can you modify this?
So instead of just considering all r greater than 0, defining some real sequence which goes to 0.
Exactly. Instead of real, you can either pick some rational, q greater than 0, q is rational. Now this sets work. Or you can also choose lots of different things. Some sequence which goes to 0 as n tends to infinity. So we can either also choose bx comma 1 by n such that n belongs to sorry n belongs to n. So there can be lots of different choices. So this works. This also works. This also works. Instead of 1 by n, you can choose 1 by 2n. Okay. So that is the reason fast countability is useful. Here, let me write the property why this is useful. So x belongs to, let x is first countable topological space. Then x belongs to some closure of a space. This is equivalent to saying there exists a sequence xn such that xn, those are element from a. Okay, xn sequence xn of formed by element of a such that xn converges to a. Xn converges to some point x which belongs to a. Sorry, not like this. There exists a sequence. So I am saying that x belongs to closure of a. Then you can, x belongs to some closure of a. Suppose this is say a and x belongs to this. This is x. Then I am saying there exists a sequence x1, x2 up to xn which converges to this. But this x, those elements are coming from this a. Okay. So this is this will be true if x is first countable, otherwise this may not hold actually. Okay, so one side will always hold, that this hold for any topological space, for any topological space, but this side, to hold this side, we need first countability. First countability is needed. And for first countable space, again, that sequential criteria, f map x to y, this is continuous. We can define continuity in terms of sequence. Okay, if for all, if xn converges to x, imply fxn converges to fx. And we already know that sometimes, means checking continuity with any arbitrary set, it is more difficult than this check. Xn converges to x imply fxn converges to fx. It is more easier to check, right? That is why first countable property is useful. Okay. Is there any doubt up to this?
No, sir. But maybe some more examples might help.
Some more
Examples, or
okay.
even non-examples.
Okay. So those are example. Another example you can see that if you choose R with lower limit topology, then is it clear that this should be first countable? Can you choose for x belongs to R, what will be your basis, local basis?
I just did maybe x comma some other element, maybe x comma x plus 1, so it's closed on x,
Yes.
open on x plus 1.
You can also choose this thing, that is x minus 1 by n, comma x plus 1 by n. This will also work, right?
Yes, sir.
Because those are open in this bx. Or you can also choose, there are lots of different way of choosing. You can, your suggestion is x comma x plus, this was your suggestion, right?
Mm.
Okay, those are actually first countable spaces. Now what about non-example? Up to this, all those metric space, lower limit topology, discrete topology, all those are first countable. Now what about non-example? So if you choose any uncountable set, for example R, and if we take cofinite topology, then this is not first countable. Okay, this is not a first countable space. Here the checking is not easier like this kind of, those kind of previous examples, but a little tricky. So in this example, how can we see that this is not first countable? So let X belongs to R. Okay. Then suppose, if possible, assume X has a countable local basis. Okay. There exists a countable basis at X. Script B at X. So Bx, it will look like this: B1, B2 up to B infinity. It will continue. Now we need to create an open set for which there is no. So we need to create an open set U which contains X, such that X belongs to U, but Bi does uh, sorry uh, no Bi does not contain any for all I. Okay, so we need to construct this open set. Okay, let us see if we can construct or not. Let Fi equal to complement of this Bi. Okay, and now choose this union of Fi. So Bi complement is Bi are open, therefore their complement must be finite, right? This is finite because B1 cannot be empty. I am not choosing empty sets. I am discarding all. There can be some empty sets, but I am not choosing those empty sets. Okay, we may also assume those Bi's are non-trivial, that is not empty. We can further assume because that is useless. I can always discard those things. So union of Fi, this is countable union 1 to infinity. So this is countable set. Now what about, so take this set X so let me draw the picture. So there are some B1, B2 like this, B3 and so on. So what is the idea? How can we create some open set which does not contain any Bi? Open set around X which does not contain any Bi. Is there any idea? How can we construct those kind of open set? Just a minute, I am coming. Sorry about this. So, is there any idea how can we construct an open set which does not contain any of this bi?
Not yet, sir.
Okay. So this is a countable set. It is clear. So let us consider let f is union of this point x with this set. Okay. So this is countable set. It is okay. Now consider r minus f. So is it possible that r minus f is empty?
No.
Okay. So not consider. So clearly, if we remove f, this is not empty. This is non-empty set. So therefore, x some y belongs to this r minus f. Okay, because this countable set, but real number is uncountable. Therefore, if we remove f, this is not non-empty. Therefore, there exists some y which belongs to r minus f, and take u to be that set, u to be the whole r minus y. Then can you see that x belongs to u? Is it clear?
Yes, sir.
Because y cannot be x, right? X is already removed here, so x is already there in f. Therefore, x cannot be y.
Yes, sir.
And you also note that bi this also not true. Can you see that this is not true? Bi cannot be contained in u.
Can you explain this last part again?
Yes. So this part is clear that X belongs to U, but Bi cannot be contained in U. Is it clear?
Oh, yes, sir.
Why?
So here U is R. Um, I've already so it's R minus Y,
Yes.
and also previously when taking R minus F, so it has already been removed there, so X
Yes.
and Y
Because
can't be the same.
yes, because Y is chosen from the intersection of all those Pi's. This Y, this is chosen from the intersection of all those things. So if that point, one point from the intersection is removed, then this set cannot contain this B2 because that point is also removed.
Yes, sir. Yeah.
One additional point other than this is removed from the intersection. That is the idea. Okay.
Okay, sir.
So therefore it is clear R with cofinite topology is not first countable. So non-examples are some tricky example, but to check example it is more easy. So let me define second countable. X is said to be a second countable space if it has a countable basis B. So note that previous property is local. So here those neighborhood are chosen corresponding to the point. So for each point there should exist some kind of neighborhood like this, some kind of B1, B2 up to B infinity. For each point those neighborhood are vary. Therefore if we take all those collection, that can be some uncountable set, right? If we take union of all those bx, this bx, script bx, union of all those bx, that can be uncountable set, right?
Yes, sir.
For example, here in discrete space, I am choosing bx equal to this singleton set. But if we take union of all those bx, then there are uncountably many points. If x is uncountable, then this whole union becomes uncountable set. Corresponding to each point, I am adding a set. So that is the problem with first countability. Second countability resolves this issue that now I am demanding a global thing, not local. Corresponding to each x, I am not demanding some countable neighborhood. In this case, for the whole x, in this case, I am demanding a countable collection of open set. Those open set which forms a basis. Is it clear?
Yes, sir.
Okay. So let me give some example, then it will be more clear. So example 1. So can you see that? So previously we have seen that R with discrete topology is first countable. Now what about R with discrete topology? Is it second countable? Can you give me any countable basis for this topology?
No, sir.
No. So this is non-example. Because any basis must contain this singleton set, because those are open. So basis mean what? Those open sets should be also contained in this singleton set. So any basis must contain all those x, for all x belongs to this real number. Okay. So in this case, the smallest possible basis is this x. Take all those singleton set. This forms a basis, but there is no smaller basis than this. This is the smallest possible basis. So this is not second countable. Though locally there are finite or countable local bases, but globally this is an uncountable set. If we take all those collection, this becomes uncountable set. Now what about R with usual topology? Is it countable, second countable?
Still no.
Still not? Okay. So in this case, I can create a basis. So take the basis a comma b, where a and b both are rational.
Oh, yes, makes sense.
So these correspond to q square, but q square is countable. Q square is, as I said, q square is same as natural number, right? One-to-one correspondence with natural number.
Yes.
So this is an example. Countable basis. You can check that all those properties of basis actually holds. That why this is a basis for R, you can check. Similarly, can you suggest me Rn with Euclidean topology? Can you give me a basis for this?
So again, I take the open balls, and R will be the rational values.
Exactly. So you can choose those open balls, but the problem is that center. How do you know that those centers are from rational points? Right. That center. So you are choosing key x comma r, where r is rational, but x can be irrational. So these correspond to some real cross r cross q. So that is uncountable set. This x and r, there are r cross q many sets you are choosing.
Yes, sir. So X will also have to be.
Yes, you can modify this. So instead of choosing x from real number, you can choose x from rational number. Okay. So that will work, but there is an more easier construction. So you know that Rn is nothing but product of n many times, right?
Yes, sir.
So this also a basis for R. A1 B1 cross An Bn, where Ai Bi both are rational. So is it clear? This is a countable basis.
Yes, sir.
So this correspond to Q cross Q. You can see this correspond to Q cross Q up to q cross q many elements. That is q to the power 2n many elements, many open sets. But as a set, this is same as saying n many open set, natural number many open set. Okay, so those are some examples. Okay, so what about other properties? Uh, so one interesting thing is that it should be clear that second countable always imply first countable. Is it clear why this should be true?
Yes, sir. So now once I have the countable basis, uh, I can use that same basis for those finding the open sets. For
Exactly. So given that countable basis, you just take all those open set which contains x. From this countable basis, choose all those bx which contains x. And subset of a countable set, this bx, if you take all those bx, that is subset of this script b, right?
yes, sir.
So subset of a countable set is countable. Therefore, from second countable, if something is second countable, that must be first countable. So you have already observed. Another thing I should mention. So similarly, you can also prove that R with lower limit topology is R with lower limit. This is also second countable. Now, what about separability? Separable space. So there is, you probably know that the definition of separability. So let me again recall. A topological space X is said to be separable if it has a countable dense subset. Okay, so what is the meaning of this? So this means there exists a subset of X. This should be countable subset, countable set, such that closure of A is X. Something is dense means the closure of that set should be the whole set. So what will be an example of this? So can you give an example of separable topological space?
So if I consider R to be X and A to be a set of rational numbers.
Exactly. So Q closure is R. Therefore, this is an example. Similarly, can you see that Rn is also separable? Rn with probably usual or Euclidean, whatever you say, or product topology of R. Can you see this is also separable?
Yes, sir.
So the closure notation is similar to complement. So let me denote by this closure, not C. So what will be A in this case?
So, considering the open bus with rational numbers as the centers and even R belonging to rational numbers.
Yes, you can choose yes. So it is like grid of rational. So I am choosing those kind of rational grids. It will be something dense, so I cannot draw, but it should look like this. Closure of this set is Rn. So this is our A. Okay, this is A. This Q is A. Can you see that cofinite topology is separable? Cofinite topology on any set X is separable. Can you see that? Can you give me a countable dense set of X? Okay, so let me put it. Let A containing X be any countable set of X, countably infinite set. So without loss of generality, I am assuming X has infinitely many points. Okay. Otherwise, that is it is vacuously true. If it has finitely many elements, finitely many points, then this is all. You can choose the whole thing. So for if it has countably finitely many points, we can choose A to be X. Okay, instead of A, we can choose X because X satisfy the property. X is countable set. So I am choosing A. A is infinite. Infinite set. I am solving the problem for X to be infinite set. Infinite set. Okay. So there exists a countably infinite subset. Is it clear? So what will be the closure of A? What is the definition? Closure means intersection of all the closed sets which contains A. Right?
Yes, sir.
So what are the open set which contains A?
A.
Is A closed? So what are the closed set in cofinite topology?
The finite sets.
Yes, either finite set or X. Those are only closed set. There are only two type of closed set, either finite or whole set. Right?
Yes, sir.
because cofinite topology is defined by complement of this, complement of finite set or complement of X, which is empty. Okay, great. Then can you see which of these closed set contains A? Can a finite set contains A?
So, yes, if I'm choosing A to be some finite set, and
Yes, if
it
you
could
choose
be
A to
closed.
be finite, then closure of A will be A because it is itself a closed set. But if A is not finite, then what will be the closure of A? Which closed set contains A? Can you see which closed set will contain A? X is the only closed set which contains A, right? Because
Yes, sir. Yes, sir. Got it.
here I have chosen A as countably infinite set.
Yes, sir. Yeah, I think I got it.
Okay. Therefore, it is okay now. Therefore, the conclusion follows because I have chosen a countable set whose closure is X. Is countably infinite set. So first note, I have not chosen any arbitrary infinite set. Then I cannot argue because I need a countable set. And I have also not chosen any finite set. Finite set is also countable, but for finite set, the closure will be itself. Closure may not be same as X. Is it clear?
Yes, sir. It's clear.
Okay, great. So what will be some non-examples? Can you see that R with discrete topology? This is not separable. So if possible, assume separable. Then what should happen? A closure should be X, right? What is closure of A? Let A contain in R. Then what will be the closure of A? So in discrete topology, every set is open and every set is also closed.
Oh, yeah. Then this would just be A.
Yes. So is it possible a countable set whose closure is R? Is it possible that
No.
A closure equal to R? This holds if and only if A equal to R. But A equal to R is not countable. Right? So this is a non-example. Can you create another non-example? Again, the same reason. R with co-countable topology. If you take any no. R with co-countable topology, that may not work. Because yes, this will work because for any countable set, countable set, closure of A will be A itself by definition, because A is closed, right?
Yes, sir.
Any countable set A closure equal to A. Any countable set is closed actually. So that cannot be same as R, which is not same as R. So those are some non-example and examples. So you can see why we are dealing with those properties. Those properties are actually topological properties. So topological properties means it is invariant under homeomorphism. So if two spaces are homeomorphic, then studying one space is equivalent to studying another space. Okay, so that's why we are studying those properties. Those properties are useful to distinguish topological spaces, and we also use those properties. In future, we'll see some how can we metricize a topological space, given topological space. So one desired thing is everything should be a metric space. This should be always desired, right? A desired property, that we always desire X to be a metric space, because metric space is always easy to study. But unfortunately, this is not true. We have already seen some topological space, for example this, which is not a metric space. Metric space is always Hausdorff, but this space is not Hausdorff. So we'll see in future that under some hypothesis, a topological space becomes a metric space. Okay, so to study those properties, we actually need this kind of axioms, countability and separations. So those are the whole thing. So one interesting thing is, this is an exercise. This is also given in Munkres. So you can look that second countable will also imply separable. If a space is second countable, then that space is separable. Okay, you can look at this property. Okay, so let me solve few problems from quotient topology and all those continuity and countability. So almost every problem from countability are like this. If that you need to see if something is countable or not. So I am not solving those kind of properties. It is already done in the examples. So let me solve some non-trivial problems. Okay. So do you want to extend this meeting or
Yes, sir.
okay? Let us solve some problems. So
I
let
will not be able to answer all the questions. I'll try,
okay.
but
It is okay. It is okay. So F is a map from R to R defined by fx equal to x when x less than 1 and x minus 1 when x greater equal to 1. Then which of the following are correct? So there are several options. Option A, f is R, so comma tau usual to R comma. So let me denote the usual topology by U script U, probably this, and lower limit by L. F is continuous, F is uh, so we write this UU continuous, means domain and codomain both are considered as usual topologies. UL continuous, LL continuous, both are lower limit, and F is LU continuous. So here L means notation. In this problem, L means lower limit topology, and U means usual topology on R. So what is your answer? Let us try to solve. So let me draw the graph. Okay. So if x is less than 1, this will look like this, right? This is fx equal to x when x is less than 1. This is 1. So when x is less than 1, this is the diagonal line. Now when x is greater equal to 1, this is just shifted. The line is now shifted. This point is actually not there, but for x is less than 1, this point will be shifted like this. A parallel line, but it is shifted. Now the question is, f is continuous with respect to usual topology. So domain is equipped with usual topology, codomain is equipped with usual topology. Now is f a continuous function?
No, not continuous at all.
So a is not true. Can you see why this is not true? So what is the definition of continuity? F inverse of any open set should be open. Can you counter this fact that here this is not true? Can you give me some open set whose image is not open? So the it is clear that problematic part should be this point 1, right?
So there was some internet connectivity issue. Can you just repeat what you told? Right now?
So if f is continuous, that means preimage of open set should be open. So can you see here that? Can you give me some example whose preimage is not open? Sorry, this should be 0. Probably this is the point actually. This is not like this. I have drawn a wrong graph. Yes.
If I consider 0, comma 2.
Yes. So this should be the problematic point. The at x equal to 1, the problem begins. At x equal to 1. This is the problematic part. So at x equal to 1, note that when x is greater than 1, the value is actually 1. Value is 0. At x equal to 1, the value is 0. But yes, so we should consider the this kind of neighborhood, right? And we should check. We should consider this kind of neighborhood and check. So f inverse of this neighborhood of 0, which is probably minus 1 comma 1, what will be this p-image?
Would be minus 1 comma 1 itself.
Yes. So I am choosing this neighborhood like this, minus 1 and 1. So can you see that the pre-image will be like this union this? Can you see that I am choosing this kind of height? So let me draw. I am choosing this height actually. So what will be the pre-image? Pre-image should be on the x-axis. So the pre-image will look like this. Not where those actually touches with this strip, right? The pre-image will look like this. Is it clear? It should be minus 1 comma 1 union 1 comma 2. Apply f on this. What will be if you apply f on minus 1 1? What will you get?
So I'm still slightly confused. How
Okay.
did they 1 to 1?
So if you draw the strip, is it clear that this strip touches strip touches here? That is cuts the straight line at those 2 points. Therefore, the p-image will be on the x-axis. This is the domain. This is the codomain, right? So the domain for which gives the value minus 1 to 1 will lies here and also lies here.
Yes, sir. Yeah, now I understand.
Okay. So you can also check by this way that fx you are checking fx less than 1 and greater than minus 1. So this is true when this will be true. When this is this or minus 1 less than 1. So there are two possibilities. First will imply this and the second will imply x belongs to minus sorry, not like this. Yes, it is okay. So I am also saying that x minus 1 should be minus 1 and plus 1 in between, but there is a condition x greater equal to 1. So the what will be the solution of those two things? The solution is this, right?
Yes, sir.
This will imply and this will imply x. So intersection of those two set gives me this x belongs to closed 1 and 2. So this will imply x belongs to minus 1 1 minus 0 comma 1, 0, 2, and this will imply x belongs to 1, infinity. So if you intersect those two sets, this will give me 1, 2. Is it clear?
Yes.
Okay. Imply either this or x minus 1, 1 and x less than 1. There are two cases. So first case will give me this set and the second case, so this is redundant, so that will give me this set and the second case will give me this. So it is clear that f inverse of some open set, this is open in codomain, but this set is not open. Is it clear?
Yes.
Not open in R with usual topology. So that's why A is not. So F is not UU continuous. Now what about LL continuous? Is it continuous with respect to lower limit topology? What about C?
Yes, sir.
Why?
Um, so again here, if I consider f inverse, I have minus 1 comma 1 union 1 comma 2.
Yes.
This belongs to lower limit topology.
But this is not enough, right?
Um, but
To check
again, these,
continuity, you need to see all such open sets. All such, it is enough to consider basis. So you need to see f inverse of some basis element is open, right? So you need to prove that fact. So instead of proving this, it is more easier to see. Can you apply pasting lemma? Can you apply pasting lemma? Let f1 is a map from this minus infinity comma 1 to R, defined by f1 of x equal to x. So here I am considering the subspace as lower limit. Both are equipped with lower limit topology. f2x equal to x minus 1. So both are continuous. It is now it is more easier to check both are continuous. Continuous. Again, you also need to apply. You need to again check that. So this is very easy. That f1 identity function is always continuous. It is easy to check. Both are lower limit topology, equipped with lower limit. And you can similarly check, because this is just shift. Shift function is always continuous. You can explicitly also check. So now can you apply pasting lemma?
yes, so
This and this both are open or closed in lower limit topology.
open.
Both are open, right? Both are open in lower limit topology. Therefore, pastings f1, f2, we get f, the desired, the given f, right? Therefore, f is continuous. So if you paste to continuous function, you will again get a continuous function. Even the domains, the restricted domains are both open or both closed. So C is correct. So we have obtained that A is false, C is correct. Now what about B? Can you conclude anything? So in B, the domain is equipped with Euclidean topology and the codomain is equipped with lower limit topology. Now can you conclude anything? Just observe this fact that F is not UU continuous. Okay. So this means you can also apply this fact that -1, 1, this is also open in lower limit topology, right?
Yes, sir.
But the preimage, is it open in U?
No.
Right? So from A we are getting the result about C. Since A is not true, B also is not true. A is not true, this will imply B is also not true. What about D? So B is not true. What about D?
Mm. So,
So any U open set is also L open set.
yes.
So you have already seen that for U open set, you have already checked that for U open set, sorry, for L open set in this option C, you have checked that for all U open set, V, F inverse V is open in L, right?
Yes, sir.
Because F is LL continuous, lower limit continuous. So in particular, if you take those V from usual topology, this will also hold.
Yes, sir.
Because usual topology is coarser, it has less number of open set than lower limit topology.
Yes, sir.
So if domain becomes coarser, so this is a fact. If domain becomes coarser, then it will again a continuous map. Okay. Otherwise, just see another interesting fact you have already observed that identity from tau. So there are two spaces x comma tau and x comma tau dash. So if tau dash is coarser, then what about the claim? What is the claim? Tau dash coarser means tau dash is smaller than this tau. Tau dash contained in tau. Then what is the claim? Identity is continuous.
Yes, sir.
So you can think. So previously it is F is LL continuous. LL continuous. So in this case you can write the problem here. F was given from this R usual for R lower limit to R usual, right? R lower limit to R usual. It this as composition like this. R lower limit, then this identity. Is it clear?
Yes, sir.
So I am breaking this F into two parts. First one is the same. So as a function, these and these are same. But as a map of topological space, those two are completely different. So the verification of C implies this F is continuous. Lower to lower is continuous. This is the conclusion of C. But identity from this coarser to identity from this finer to coarser. This is lower limit is finer. This is coarser. This is finer to coarser. Identity from finer to coarser is also continuous, right? This is very easy to check. By definition, tau dash is subset of tau. Therefore, if something is open here, that preimage U is open in tau dash means U belongs to tau dash. The preimage is U, that also belongs to tau by definition. Tau dash contained in tau, right?
Yes, sir.
So the composition F becomes continuous. Therefore, so both are F. So let me denote it by some. So this red F. Okay. So this red F is continuous as composition of two continuous function is continuous. Two continuous functions. So similarly, you can also prove that A is not continuous, imply B is not continuous, because you can again use that fact. So here UL, you can factor UL as, so we have RU comma RL. You can factor this as RU to RU, then RU to RL, right? So if B is true, that UL continuous, then that should be also true, because this identity map is continuous. Therefore, if B holds, then A should also hold. So contrapositively, A is not holding, therefore B will also not hold. Is it clear?
Yes, sir.
Okay, maybe it seems very confusing, but just try yourself. It will be easier than what is. Okay, the main thing is done. So let me solve one problem from quotient topology. Okay. So that problem is actually given in Munkres. You can see that a map R from X to A be a continuous map such that there exists a continuous map F from A to X with R composition F is identity. Then the conclusion is R, you need to check R is a quotient map. This is the conclusion. So how do we check if something is quotient or not? So recall a map Q from X to Y. This is said to be a quotient map between two topological space. If it is surjective, continuous, so continuous will be already be in the condition that F inverse of some open set, F inverse of V, this is open if and only if V is open. So it is more than continuity. Continuity in the definition of continuity, if V is open, F inverse V is open. That is the definition. But in this definition, if F inverse V is open, then the reverse is also true. F inverse V open will imply V open. So it is more than continuity. Is it clear?
Yes, sir.
So we need to prove that this R is a quotient map. So how do we see R is a quotient map? Okay. So R is continuous, this is already given. Okay. So one side is already given that R. So here R is a map from A to X. So it is continuous. This will imply R inverse U. This is open for all U open in X. This is the definition of continuity, right? Now you note that F is also continuous, right? Since F is continuous, this will imply if you take inverse image of this open set, this is open, right? So if you again take inverse image of this open set, this become open, right? Now the interesting fact is that F inverse R inverse, this is same as R composition F inverse of E. You know this fact, right?
Yes, sir.
But R composition F is identity. So this is identity inverse of U by star. Star will imply this, and which is same as U. So I am getting the reverse thing, that is so one side is given. I am assuming let R inverse U is open. Then the conclusion is U is also open. This is the conclusion. So I am starting with R inverse U is open. I am getting U is open. Is it clear?
Yes, sir.
So if U is open, then by continuity R inverse U is open. But conversely, if we assume R inverse U is open, then this kind of argument will show that U is also open. Okay. So is it clear R is quotient map? R is surjective. Is it also clear that R is also a surjective map? Composition of two map is identity. That will always imply the beginning map is injective.
Yes,
Yes.
it's clear.
Okay. R compose F is identity. This will imply R is surjective. So the all properties of quotient is holding. Therefore, R is a quotient map. So this kind of map is actually called retract. A retract map. So it is, for example, let me draw a picture. It will be more clearer. So this center of the disk, you can think this center as a disk of the disk as a map like this. The point included in disk, right?
Yes, sir.
This point, the singleton set, include the singleton set inside the disk. This is the map. You can define a map like this. P goes to P, f of P equal to P. So can you uh, give me a map in the reverse direction? So the map in the reverse direction is like send every point to the singleton P. R of everything equal to P for all x belongs to the disk. And note R composition F is actually identity. So retraction is this surjective map. Send everything to the point. Okay, it is like shrink everything to the fixed origin. So this kind of map is always, this R is always a quotient map. This appears lots of time. So this is quotient map. Let me solve an example using this argument. How can you show something is quotient? So explicitly checking that R inverse U is open if and only if U is open. This is actually hard. That R inverse U is open if and only if U is open. It is hard. But using this argument, this becomes easier to check if something is quotient or not. So here the problem number 3 in Mooncrest, here uh, there is a map given pi 1 from this R cross R to R. This is Mooncrest, page 135. Pi 1 is a map from R cross R to R given by the projection on the first component. Okay, given by pi 1 on x comma y, this is just x. Project on the first component. And A, this is a subspace of R cross R. It is defined by this. Explicitly A is x comma y, all those points such that x is greater equal to 0 or y equal to 0. Okay. then you can always obtain a restriction map. The restriction map Q, this is the map from A to R. So A is a subspace of R cross R. So you, from this projection map, you always get a map on A, right? You just restrict everything on the subspace A. Now you need to prove so that Q is quotient map but not open, neither closed. So neither open nor closed. Whatever. Neither open nor closed. Can you show that this map is actually a quotient map? How can you show that?
The neither open nor closed part is clear.
Can you see why it is not a open map? So let me draw the picture. The picture is like this. So y equal to 0 represent this line, right? So the domain is like this. The set, I am drawing the set A. A is this x-axis, and x greater equal to 0 is represented by this kind of so this is the domain. This is the domain, and the map is projections. Take any point, map it to this x-axis. For example, here all those points are fixed, and if you take something here, it maps to this point. F of this point, f of x comma y, this goes to x comma 0. That is on the real line, this is simply x. So can you show this is not a open map? So open map means every open set maps to a open set. Okay. Open maps, the definition of open maps means f of open set is open. So can you give me some open set which is not, whose image is not open? Let us consider this set, this thing. So the question, is it open in A?
Yes. We are again taking the usual topology, right?
Yes. Yes, usual topology. I am considering usual topology on both sides. So why this is open? This greater equal to 0, that is open.
So if I take any uh, sets x comma y, since uh, since I'm considering x greater than or equal to 0, all the x values I could so they are also greater than or equal to 0. So
So we need to see that this can be written. If can we can this can be written, can it be written as a intersection some open set, a intersection u, where u is open in R2, R square.
uh, a intersection so see if I take 0 comma infinity,
Yes.
then uh, I know that 0 comma infinity is open.
So I am considering the whole thing, this side, including the y-axis. So this whole thing I am considering. Okay. So
So
I need to
open set 0 comma infinity.
yes,
Uh,
open set 0 comma infinity you are considering.
yes, sir.
Then, but this is not open in A, right? This is not open in A.
Yeah.
If you only consider this line, sorry. If you only consider this line, this is not open in A. So let me just change a little bit. Uh, Here the problem can be there is there will be some problem because of the origin. So let me remove the origin. Okay, remove the origin. Okay, let me remove the origin 0 comma 0 point. Now note that this can be written as open set with, can you see that u intersecting with A give me this set? Hmm? So let u equal to minus 1 by y.
Not audible.
One. So I am considering these 2 points, this thing and these two things, and I am taking the whole like this as u. sorry. So I am taking. Okay, let me write. So I am taking U as. Can you hear me? Hello.
Sir, the audio is getting cut a lot. No, it's not quite
Oh,
up.
okay. Okay. Can you hear me now?
Yes, sir.
Okay. So I am saying that take U as this kind of open set. So let me draw the picture. It is more easier to draw. U equal to this picture. So take this, and this side. Okay, let me write more easier open set. So take U equal to this upper half plane. Okay, is um, x comma y such that x greater equal to 0 and y is strictly greater than 0. So question, is it open in A? So is U open in A? Is it open in A?
Yes, sir.
So how do you intersect with open set? A intersection some open set in R2. Can you give me some open set from R2? Can you see that this is open in R2, this set? This is open in R2. So this U can be written as intersection of this upper half with the given set A. Is it clear?
Yes, sir.
And therefore it is open because U is written as A intersection some open set in R2, right? Therefore this is open. Is it clear? But what is the image of this U? What is the image of this U? So I am considering this, this as the set U. So what will be the image of U? U projects everything on the x-axis, right? Sorry, not F. It is actually the map is Q. So you can see the map Q of U. This is actually cosine map. Sorry, we need to prove. So Q acted on U. This can be written as open 0, infinity, which is a subset of R. So there are lots of points. For example, those points also move maps to this 0. So I am getting this whole line. Is it clear?
Yes, sir.
So there are some open set whose image is not open in R. This is not open in R. In the range, in the codomain, this is not open. So therefore Q is not open map. Now what about closed? Is it closed? Can you create an example by which you can say that Q is not a closed map? The first part is okay. So consider this y equal to 1 by x. So let f equal to this set x comma 1 by x, those kind of point, such that x belongs to R. Not x belongs to R, x is positive. So I am taking this graph x comma 1 by x, this graph. So this is actually closed in R2, right? It is an easy exercise. You can always show that any graph is closed. So you can see that this graph is closed. You can also explicitly see from this picture, this f is closed in A. Now what is the image of this f, q of f? Will this hand, will it touch this uh, y-axis?
No.
This will never touch. So if you take the projection of the whole thing, it will land here, right? 0 to infinity.
Yes.
So q of f is 0 to infinity. This is not closed in R. So q is neither open nor a closed map. So we need to see that q is quotient map. How can we see q is quotient? So one argument is like this. We can always prove something is quotient or not by retraction argument. So we need to construct a map in the reverse direction. Okay. Such that Q composition F is identity. So here consider the inclusion map. Consider the map F from this R to the given A defined by f of x equal to x comma 0. So what I am doing? I am considering a map from this real line. Just send every point to the x-axis. Is it clear? What is the map? And this map is actually a continuous map. Okay.
Yes.
It is just R2 R2. This map is continuous, and I am just restricting on the codomain. So I am just changing the codomain. So this is continuous. The map. So this is continuous. Now another thing, R compose F. So R compose F on X. So f on x is x comma 0. So this is R acted on x comma 0. But what is the definition? R on x comma 0, what will be that? Sorry, here the map is Q. This is not R. Q is the projection map, right? Q on x comma y, this is actually x. Therefore, Q on x comma 0 will be x. So Q compose F is identity map. Therefore, Q is a quotient. So you can use the same idea to show the next problem. That is, in the next question, there is some equivalence relation, and you need to prove the what is the quotient space. Again, you can use the same idea. you can construct two functions. One function is q, another is a, and you need to use this kind of relation. Q composes F is identity by which you can prove that Q is quotient. So okay, let us stop here. It is 8:52. So is there any question?
No, sir. I think I just need to get used to the definitions so that I can understand easily, but there's no doubt as such.
Yes, there are lots. Okay, then thank you. We'll meet again on the next Friday. Thank you very much.
Thank you, sir.